Dear students, today I am going to teach you relations of class 12th. You have already learned the meaning and definition of relation, some kinds of relations, how to represent a relation in terms of ordered pair in class 11th. In class 12th, you are going to learn equivalence relation and equivalence class. Before going to enter in class 12th, let us have a first work on class 11th syllabus. So, I will start with Cartesian product. So, Cartesian product of two sets. Suppose A and B are two non-empty sets. Suppose A and B are any two non-empty sets. Then the Cartesian product of A and B, denoted by A cross B. Cartesian product of A and B is denoted by A cross B, is defined as the collection of all ordered pair AB such that A belongs to A and B belongs to B. That means this A cross B is the set of all ordered pairs AB, where the first element of this ordered pair is an element of this first set and the second element of this ordered pair is an element of this second set. If we find B cross A, then this B cross A will be the collection of all ordered pair BA, where this B is an element of first set B and A is an element of A. So this is all about ordered pairs. Let us have one example. If A be the set of two elements AB and B be the set of three elements, suppose 1, 2 and 3, then we can define or we can find A cross B in terms of ordered pairs as we'll collect all those ordered pairs in which the first element of the ordered pair will be an element of first set A and the second element of the ordered pair will be an element of the set B. All possible such collections is A cross B. That means, so the first element I can take A from this set A and 1 from this set B. A1 is an element of A cross B. A2 is another element of A cross B. A3, B1, B2, B3. So this completes the set and this set represent A cross B. Now come to relation. You know the definitions of relation. So relation. So a relation from A to B, a relation R from A to B is a subset of A cross B, is a subset of A cross B. Every subset of A cross B is a relation from A to B. If we consider, suppose this A is same, you consider A, B, and suppose B is the set 1, 2, 3. 1, 2, 3. Suppose R1 is the collection of A1, B1, A3. Now we have to verify whether this R1 is a relation from A to B or not. So what this definition states, a relation R from A to B is a subset of A cross B, or in other words we can say every subset of A cross B is a relation from A to B. So we have to verify whether this R1 is a subset of A cross B or not. Let us define A cross B. A cross B is the collection of all A1, A2, A3, B1, B2 and B3. We have to verify whether this R1, which contains three elements A1, B1 and A3, is a subset of A cross B or not. If this R1 is a subset of A cross B, then it is a relation from A to B, Otherwise, R1 is not a relation from A to B. So here it creates that this R1 is a subset of A cross B. Therefore, this R1 is a relation from A to B. Let us start the syllabus of class 12th. So in class 12, equivalence relations is there, but before going for equivalence relation, let us discuss the first kind of relation, that is reflexive relation. Reflexive relation. So what is the meaning of reflexive relation? Let us define this. So a relation R in a set A is said to be reflexive, is said to be reflexive if and only if the order pair AA belongs to R for every A belongs to A. For every A belongs to A. That means a relation in A is said to be reflexive if and only if the ordered pair AA belongs to R for every A belongs to A. So this line is most important, for every A belongs to A. Let me explain this with an example. Let us consider a set A. A is suppose 1, 2, 3. 1, 2, 3. And our aim is to find a reflexive relation in A. Suppose, let us define R1. I want to make this relation R1 reflexive. So before that, let us consider this line for every A belongs to A. For every A belongs to A, what does it mean? Now in this case, A is the collection of only 3 elements, 1, 2 and 3. For every A belongs to A, we have to decide first. So what are the values that can be assigned to A? That means A can be taken as, what are the possible chances of A? So A, we can assume this A as either 1 or maybe 2, or this A may be 3. That means this A value of A for every, because it is for every, not for some or any other. So for every A belongs to A. So for every means we have to consider each and every element of A. So this A can take the value of 1, 2 or 3. If A is equal to 1, now if for every A belongs to A should be the element of R. Or in other words, we can say this A is related to A. That means every element is related to itself. Every element of A is related to itself. That means this relation R1 will be reflexive only when if 1 is related to 1. 1 should be there. Now if A is equal to 2, then 2 is an element of R. If A is equal to 3, then 3 is an element of R. So in addition to this, that means R1 to be reflexive, this R1 will be reflexive only when it contains at least these 3 elements, 1, 2 and 3. Other than this, it may contain some more elements, no problem. But definitely these 3 elements, 1, 2 and 3, these 3 elements must be contained in R1 to be reflexive. So after that, you can take any other elements, some more element you can take 1, 2 or 3, 1 and so on. That means R1 will be reflexive only when 1, 2 and 3 are the elements of R1. So now you consider R2. R2, suppose R2 is the collection of 1, 1, 2, 3, 2, and 2. Okay, you consider only 4 elements. Now this is R1, R2. Now check whether this R2 is reflexive or not. How can we verify whether this R2 is reflexive or not? Now you observe this A1. A is the collection of only 3 elements, 1, 2 and 3. And the definition states that for every A belongs to A should be an element of R. So if we take A as 1, 1 1 should be an element of R. Yes, this 1 1 is an element of R2, no problem. If A is equal to 2, then 2 2 is an element of R2, no problem. Now if A is equal to 3, then 3 3 should be an element of R2, so that this R2 will be reflexive. But here 3 3 doesn't belongs to R2, therefore R2 is not reflexive. R2 is not reflexive. Though it is a relation, but it is not a reflexive relation. Let us consider some more examples. Let A be the set of all straight lines in a plane. A be the set of all straight lines in a plane. And suppose R is a relation in A. R is a relation in A defined as R is the collection of all ordered pairs L1, L2 such that L1 is parallel to L2. L1, L2 belongs to A. So we have to verify whether this relation is reflexive or not. Under what condition this relation will be reflexive? This relation will be reflexive if for every L belongs to R, for every L belongs to A, this LL should be an element of R. Only then the relation will be reflexive. Now we have to verify whether every element of this set A is related to itself or not. That means, can we say under what condition every element will be of A will be related to itself? Now the relation you can verify here. You can see L1 and L2 is an element of R only when L1 is parallel to L2. That means under what condition LL will be an element of R? If this LL will be an element of R if the L is parallel to L. So we can clearly state that every line is parallel to itself. Therefore, since L is parallel to L for every L belongs to A, then we can say this LL is an element of R. Therefore, L is reflexive. Now, if we change it slightly, now you just change the relation. Suppose R is a relation, and R is the collection of all ordered pair L1 L2, such that this L1 is perpendicular to L2, where L1 L2 belongs to A. Now check whether this relation is reflexive or not. This relation will be reflexive only when every element of A is related to itself. Every element of A is related to itself. It means for every L belongs to A, LL should be an element of R. And under what condition LL should be an element of R? LL will be an element of R if L is perpendicular to L. Can we say every line is perpendicular to itself? No, this is not possible. So we can say no line is there which is perpendicular to itself. That's why this relation LL doesn't belongs to R. Therefore R is not reflexive. If we consider one more example, let us have one more example with numbers. So suppose R is a relation in Z, set of integers. Z means set of integers, defined as R is the collection of all ordered pairs AB such that A minus B is divisible by suppose 5. Divisible by 5. So we have to check whether this relation is reflexive or not. Okay. So before going to check whether this relation is reflexive or not, let us verify under what condition two elements, suppose xy belongs to R or not. Under what condition this element xy, this order pair xy will be an element of R, or in other word we can say under what condition an element x, an integer x will be related to another integer y. That means we write in this way, x is related to y. Under what condition? The condition is given here. So x is related to y only when x minus y is divisible by 5. X minus y is divisible by 5. So let us take some example. So is 1 2 an element of R? Check. 1 minus 2 is equal to minus 1, which is not divisible by 5. Therefore this 1 2 is not an element of R. So is 5 15 an element of R? So 5 minus 15 you check. 5 minus 15 is equal to how much? Minus 10. Yes, minus 10 is divisible by 5. Therefore 5 15 is an element of R. We have to check whether this relation is reflexive or not. So the relation will be reflexive only when every element of this set Z is related to itself. So if we consider any element A, suppose this A should be related to itself, or in other words we can say AA is an element of R. If AA is an element of R, then only the relation will be reflexive. So under what condition this A will be an element of R? This A will be an element of R if A minus A is divisible by 5. And what is the value of A minus A? A minus A is 0. And we know 0 is divisible by 5. That's why the relation is reflexive. But now, how can we verify? So you go through like this. For every A belongs to Z, A minus A is equal to how much? 0. And which is divisible by 5. Therefore, since this A minus A is divisible by 5, according to this definition, A minus B is divisible by 5, then AB is an element of R. X minus Y is divisible by 5, then XY is an element of R. A minus A is divisible by 5, then the order pair AA is an element of R, hence R is reflexive. Now come to second kind of relation, that is symmetric relation. Symmetric relation. So let us define this symmetric relation. A relation R in A is said to be symmetric if and only if the order pair AB belongs to R implies that BA belongs to R for all AB belongs to A. Now, symmetric relation states that under what condition this relation R in A is said to be symmetric? If and only if AB belongs to R implies that BA belongs to R. What does it mean? If A is related to B, then B must be related to A. If A is related to B, then B must be related to A. So let us take some example. Suppose A is the collection of all the students of DAV Public School Chiriveri, all students of DAV Chiriveri, and suppose R is a relation. R is defined as the collection of all order pair AB, such that A is a friend of B. A is a friend of B. Now, A is related to B. The order pair AB belongs to R. The order pair AB, if let assume that AB belongs to R. If for all AB belongs to R, and if it conclude to BA belongs to R, अगर A B से related है एंड बी, इससे अगर हम पहुंच जाते हैं कि B is related to A, then the relation will be symmetric. That means now you consider under what condition AB is an element of R. AB is an element of R if A is a friend of B. If A is a friend of B, then A is related to B. A is a friend of B. Since A is a friend of B, can we say B is a friend of A? Naturally, if A is a friend of B, both of them are friends, so B will be definitely a friend of A. So we can say, which implies that B must be friend of A. And since B is a friend of A, we can say BA belongs to R. BA belongs to R. That means if A is related to B in this relation, if A is related to B, then BA must be related to B must be related to A. That means AB is an element of R, then BA must be an element of R. So this relation is a symmetric relation. This relation A is a friend of B under this condition is a symmetric relation. Let us consider one more example. Suppose A with the same set, मैं थोड़ा सा इसको चेंज कर रहा हूँ. Suppose A is the collection of all the students of DAV Cherry and R is the relation such that it is the collection of all ordered pair AB such that A is the brother of B. The brother of B. We have to check whether this relation is symmetric or not. This relation will be symmetric if A is a brother of B, then B must be a brother of A. Then only the relation is symmetric. But if A is a brother of B, can we say always whether B is also the brother of A? No, this may not happen. If A is a brother of B, this B may be a sister of A. So this B may not be brother of A. That's why this relation is not symmetric. So if we consider some more example, let us consider the same example we have taken in reflexive. A is the collection of all straight line in a plane, and R is the collection of all ordered pair L1, L2 such that L1 is parallel to L2, L1, L2 belongs to A. Now check whether this relation is symmetric or not. Symmetric if L1, L2 belongs to R, then L2, L1 belongs to R, then only this relation will be symmetric. So under what condition let us assume that let L1, L2 is an element of R. Under what condition L1 and L2, the ordered pair L1, L2 will be an element of R. This will be an element of R if L1 is parallel to L2. And without loss of generality, we can say if L1 is parallel to L2, then we can say L2 must be parallel to L1. And since L2 is parallel to L1, then this ordered pair L2, L1 belongs to R. Therefore, this relation R is symmetric. This relation R is symmetric. In a similar way, we can take one more example. Suppose R in Z, R is a relation in Z defined as R is the collection of all ordered pair AB such that A minus B is divisible by 5. We have to check whether this relation is symmetric or not. Let us consider this relation now. Let AB is an element of R for all AB belongs to Z. Under what condition AB will be an element of R? This AB will be an element of R if A minus B is divisible by 5. A minus B is divisible by 5. If A minus B is divisible by 5, can we say B minus A is divisible by 5? Naturally, so if we take A is equal to 5 and B is equal to 10, suppose. A minus B is equal to how much? Minus 5, which is divisible by 5. However, B minus A is 5. That is also divisible by 5. Since A minus B is divisible by 5, we can write A minus B is equal to 5k for some k belongs to Z. For some k belongs to Z. And since A minus B is equal to 5k, we can write B minus A is equal to minus 5k and which is equal to 5 into minus k. since k is an integer, minus k must be an integer, and this b minus a is in terms of 5 into an integer, so we can conclude that b minus a is divisible by 5, and which implies that this ba is an element of R, and which conclude that this relation R is symmetric. So you go through these two topics, and in my next class I will teach you some more kinds of relation, that is transitive relation, equivalence relation, and also I will consider equivalence class. Thank you.